In this example problem, what we're doing is we are told that the Earth has been sending out radio signals for the last 100 years, and those radio signals will travel away from the Earth at the speed of light. They fill the surrounding volume of space, and eventually they're going to pass some stars, and there might be someone living in that star system that could pick up our radio broadcasts and start repeating our memes and catchphrases. So, how do we want to think about this problem? Let's say here is the Earth. Technically, the Earth travels around the sun, but the size of the Earth's orbit compared to light year distances to stars is just incredibly tiny. I could just pretend the Earth is a point for the context of this problem. Now, if we send a radio signal out, then we're going to send it evenly in every direction. And let's say 10 years later, the radio signal has traveled this far. But it traveled this far in every direction evenly. So this radio signal is going to be filling a sphere as it expands. The radio signal is like a spherical shell that's growing bigger and bigger as it travels away from the Earth. So there is a spherical shell of a radio signal that is here. We emitted this signal 10 years ago, and it's spreading out through the universe roughly in the shape of a sphere. But 20 years ago, we also sent out a spherical shell, a radio signal, and that radio signal had more time to travel, so it will have had more opportunity to travel further away. So 20 years ago, there was a signal that now got this far away from the Earth. And 30 years ago, we sent out a signal, and that signal is now this far away from the Earth, and on and on. So we have these ever-increasing spherical shells that are moving away from the Earth at the speed of light, filling the volume of space surrounding our solar system. So let's draw this picture to be smaller, and let's say here is the Earth at the center of this sphere. And we'll say we began broadcasting 100 years ago. It was a little bit more than that, but quick hand-wavy estimate. And so 100 light years away, the signals that we broadcast 100 years ago are barely just arriving today. So here is the Earth at the center of a ever-expanding sphere. Today, that sphere is 100 light years in radius. Now, we're told that there are 1.4 times 10 to the negative 4 sun-like stars per cubic light year. So I'm going to write this as rho is equal to 1.4 times 10 to the negative 4 sun-like stars per cubic light year. Okay, so what did I write here? How are we thinking about this? The first thing I'm going to say is this thing that looks like a lowercase p is actually the Greek letter rho. So this is actually rho, which is Greek. And very often in physics, rho is associated with some type of density. It could be mass density, or it could be some other type of density that we talked about in the slides. Also, at the same time, we could ask, what is the density that I'm talking about in this problem? Well, I have rho is equal to 1.4 times 10 to the negative 4 sun-like stars per cubic light year. So the number of sun-like stars is the quantity of interest, and the cubic light year is the geometric term that we're going to talk about. So I'll say 1.4 times 10 to the negative 4 sun-like stars per cubic light year, which I'll write as light year cubed. Well, I look at this and I see rho is a number less than 1. Does this make sense? How could we have less than 1 star per cubic light year? And the way we accommodate that is I'll draw a 2D picture, but the same principle will hold in 3D. Let's say each square in this picture is 1 square light year. So here I have 25 square light year total. And I'm going to put some objects in this grid. So here's an object, here's an object, here's an object, here's an object. I have 4 objects in 25 square light year. So 4 objects in 25 square light year. So if I say 4 out of 25, that's 16 out of 100. So I could think of that as 0.16 objects per square light year. So when I have a density less than 1, that just means not every individual cell will have an object in it. So in this case, I do not have 1 star per cubic light year. I have to look at several, or in this case, many cubic light years before I expect to find 1 star. And we're assuming they're more or less evenly distributed. So what we're dealing with here is the exact same idea as what we're dealing with here. The only difference is this is 2D, this is 3D, but nothing really changes. So the first question I'm going to ask is, how many total sun-like stars are in this entire volume? So how many total sun-like stars are in this volume? And at that point, if I could answer that question, then 5% of this number will be the final number we're trying to find for how many civilizations we found. So how many sun-like stars are in this volume? Well, density I am thinking of as density equals total number of stars total number of sun-like stars, if I'm running out of room, over the total volume. Okay, the density, we already know what that is. This is the density, so this is the number I want here. What's the total volume of this entire region? Well, to answer that question, I look at this picture and I see the total volume of this region is going to be a sphere. So that's basically asking, what is the volume of a sphere with a radius of 100 light years? So to answer that, I would go to Wikipedia or Google or an appendix or the cover of a textbook. I look up what is the volume of a sphere, and the volume of a sphere, volume SPH for sphere, is 4/3 pi r cubed. Now, very often we would, I tell you for problems, you want to convert to meters, your base SI units. In this problem, I am not going to do that because we would have to convert right back anyway, and that would just be an extra annoying step. So the total volume of this entire sphere, I could write as 4/3 times pi times 100 cubed. And at this point, I'm going to put that number in a calculator. When I do, the total volume of this sphere is 4.19 times 10 to the 6 cubic light year. So at this point, we have the density, we have the volume of the sphere in total. So I have enough information to find the total number of sun-like stars in this sphere. So I could say then that 1.4 times 10 to the negative 4 is equal to the total number of sun-like stars divided by the volume. The total volume is that 4.19 number, 4.19 times 10 to the 6. At this point, I personally prefer that I don't like writing units when I work through a calculation. If you want to write units when you work through a calculation every step along the way, that is just absolutely fine. If you prefer not to, that's fine too. Do whatever you're more comfortable with. Just remember, at the end of the day, make sure you do know what units you should be working at. So at this point, I multiply both sides by the 4.19 number. So I get 4.19 times 10 to the 6, 1.4 times 10 to the negative 4 is equal to the total number of sun-like stars. And at this point, I can multiply these two numbers together, and I will get a number that is 586.6. 586.6 is equal to the total number of sun-like stars. So we are told that about 5% of these 586.6 stars actually have a civilization around it. So first of all, what do I mean by a decimal point for the number of stars? Well, you could think of this number as the expected number of stars you could find if you were to actually count the total number of sun-like stars. At the end of the day, you could only have a whole number of stars. You can't have a fraction of a star. But if you were to actually go and count the number of sun-like stars in this entire region, maybe you would count 586, maybe you would count 587. But stars are going to be distributed randomly, and random does not mean evenly distributed. So maybe you'd find 590 or 580. This is just an estimate for how many stars you would expect to find on average. So 5% of these stars have a civilization that is listening to the radio waves. How do I address that? Well, that's basically asking what is 5% of that number? And I could write that as number of civilizations is equal to 0.05 times 586.6. And at that point, if I go to a calculator, the number of civilizations that are repeating our catchphrases and memes will be 29.33. So again, this is the expected number of sun-like stars our radio broadcasts have reached, and we expect there are about 30 species of aliens and civilizations repeating our catchphrases and memes. How did I come up with this 0.05 number? How do I convert 5% to the 0.05? To demonstrate that idea, let's just pick an easier number to work with. Let's say 200. So if I were to say I have 200 objects, if I multiply that number by the number 1 times 200 is equal to 200. This is like saying 100% of this, my original number of objects, gives me my original number of objects. If I were to say what is 25% of my original number, I could write that as 0.25 times 200, and 0.25 times 200 gives me 50. So 25% of my original number, I multiply by 0.25. If I want to know what is 5% of 200, I would do 0.05 times 200 equals 10. So 5% of 200 is 10. In a way, I could kind of think of a percentage as multiplying by a 2-digit decimal number. So I could think of this as 1.00, and therefore this is 100%, this is 25%, and this is 5%. And you could extrapolate this to any number at all, 16%, 64%, whatever.